Hello, everyone, and welcome to the EC2 Inf1 Instances webinar. My name is Gadi Hout. I am a Senior Director of Product and Business Development here at AWS. As a background, I will cover the reasons why we created Inf1 specifically optimized for machine learning inference workloads. I will then dive into the underlying software and hardware technology that is enabling these new instances, and also describe one of our first customers started using the Inferentia instances, Alexa text-to-speech, talk about their experience with these unique and powerful instances. So let's get right to it. At AWS, companies from every imagined industry segment are working with us to build machine learning solutions that are core to their business. It's a broad and fast-growing group that includes companies like NBC Universal, Snap, State Farm Insurance, Intuit, F1 Racing, NFL, Coinbase, Convoy, Sony Interactive, and many, many more. For example, in the healthcare space, companies like Cerner are tapping into AWS's deep portfolio of machine learning and AI services to surface insights that will help their customers streamline operations and provide more personalized patient care. NASCAR uses Amazon SageMaker recognition and Amazon Transcribe to enhance metadata and captions for their new video series, saving thousands of hours of manual search time and better servicing video clips to their 80 million fans. When we sat down to think of what type of ML solutions our customers need the most, the first question we asked ourselves was, what are the main use cases from an infrastructure perspective that is driving ML workloads on AWS? We learned that machine learning applications are growing in sophistication and becoming more expensive to run in production. This is driven by the need to provide a richer and more personal customer experience. Although there is a lot of market focus on reducing the cost to train machine learning models, majority of our customers say that running ML inference in production is where they see most of their overall application infrastructure cost. As an example, here at Amazon, about 90% of the cost of running machine learning applications is spent on inference. And we keep seeing this pattern with many other customers. Therefore, we decided to build an instance offering that is focused on increasing performance and lowering costs for our customers, specifically targeting inference. To do that effectively, we had to build a new class of AWS chips, cutting-edge silicon devices we call Inferentia. Inferentia and the system around it was built from the ground up to provide the highest performance at lowest cost, focused solely on machine learning inference applications. Today, Amazon EC2 offers multiple options for machine learning inference to our customers. Customers running machine learning models that are sensitive to inference performance and cost can use Inf1 instances. These are powered by our custom-built Inferentia silicon. As you will see later today, Inf1 instances are the fastest and lowest cost instance for machine learning inference in the cloud. Secondly, for ML models that require access to NVIDIA's libraries, such as CUDA and TensorRT, we recommend using the G4 instances that are powered by the NVIDIA T4 GPUs. And lastly, for those ML models that are less sensitive to inference latency and are low throughput in nature, customers can use the EC2 C5 instances. These are powered by custom second-generation Intel Xeon scalable processors and utilize the AVX 512 VNNI instruction set. But of course, today we will focus on the Inf1 instances and Inferentia. Let's start from the Inferentia chip. We designed Inferentia to solve one problem really well. Inferentia is a high-performance, low-power inference workhorse. Each Inferentia chip is providing more than 100 tera operations per second at low power, which allows us to pack up to 16 of them in a single server, providing more than 2 peta operations per second. Let's think about it for a second. 2 peta operations per second is more than double the performance of our biggest NVIDIA GPU P3 machines. Each Inferentia chip has 4 neuron cores. A neuron core is a high-performance systolic array matrix multiply engine. Each neuron core has a two-stage memory hierarchy, a very large on-chip cache, and an external commodity DRAM. These chips are also implement a fast interconnect technology that allows us to connect all of them to a large virtual device. And I will discuss why this is useful soon. Inferentia supports multiple data types, int8, floating point 16, and bfloat 16, and can be used from all popular machine learning frameworks, PyTorch, MXNet, and TensorFlow. We also designed the Inf1 servers themselves. Combined with our Nitro subsystem technology, they provide the highest throughput and lowest cost machine learning inference instances in the cloud. The Inf1 instances are optimized to serve a variety of machine learning inference use cases like image classification, object detection, natural language processing, speech recognition, search, and fraud detection, among others. They are useful to customers who are looking to increase their ML application performance and reduce the cost of running these models. We fully expect that lowering the cost of ML will be a major drive in having more applications adopt ML capabilities and provide overall better experience to these applications and users. As already discussed, the EC2 Inf1 instances feature the AWS Inferentia chips, as well as AWS Neuron. AWS Neuron is a new software product that natively integrates into popular machine learning frameworks and optimizes performance for the Inferentia chips. And as I mentioned earlier, Inf1 instances feature AWS Nitro, as well as custom second-generation Intel Xeon scalable processors and up to 100 gigabits per second of networking to enable high-throughput inference. The EC2 Inf1 instances are available in 4 sizes: 1XL, 2XL, 6, and 24XL. The 1XL and 2XL are single chip instances, single Inferentia chip, and the 6X large and 24X large are multi-chip variants. Inf1 instances will also be supported in AWS managed services such as SageMaker, Amazon EKS, and Amazon ECS. I have mentioned performance and cost a few times already. Let's look at some numbers that we measured. In this example, we run BERT-based model to benchmark performance. BERT is a natural language understanding model, and this inference performance test follows a real-life end-to-end use case and is not a synthetic lab experiment designed to showcase a hardware capability. These are actual real-life results. The test is running using TensorFlow, which shows the largest Inf1 instance, the 24XL, and the largest G4 instances, the 12XL. These results show 4x higher throughput and overall 54% lower cost per inference on F1 compared to the G4 instances. It's important to note at this point that prior to launching Inf1, G4 was the best price to performance instance option in the cloud for machine learning inference. And now we improve it significantly with the Inf1 instances. AWS Neuron is the SDK providing tools and drivers to develop, deploy, and profile Inferentia accelerated inference applications. It is designed from the ground up to allow for maximum scalability in optimizing both for highest throughput and lowest latency for a wide variety of use cases. Neuron has 3 main components: an ahead-of-time compiler, a runtime driver, and profiling tools, which we will discuss in detail. Neuron is pre-integrated into popular machine learning frameworks, including TensorFlow, MXNet, and PyTorch. It supports commonly used machine learning models such as ResNet for image recognition and classification, and BERT for natural language processing and translation. If you already run applications through one of these frameworks, either on CPU or GPU, you will find a familiar environment to accelerate your machine learning application with Neuron. Neuron comes pre-installed in our AWS Deep Learning AMIs, or you can pip install it into your own AMI. Instructions are available on our GitHub, alongside with other detailed tutorials, technical briefs, and reference manuals for those who wish to fine-tune their applications. In most cases, though, we see customers change a few lines of code to get their framework to enable Inferentia and start running their inference applications. Finally, for support, we encourage you to look for information over the GitHub, detailed documents, and tutorials, and you can also reach out to our team via the support forum, or use the GitHub issues, or even open a ticket with the AWS support team. As I described, to start using Neuron, you can pick up the AWS DL-AMI image or install Neuron on your own AMI with a pip will apt-get commands. And the Neuron GitHub has detailed instructions how to install and run Neuron. For example, if you use TensorFlow for computer vision classification models on EC2 G4, or use PyTorch to run natural language understanding models like BERT to improve your question answering applications, you may make a few changes to indicate that to the framework that the new target device is Inferentia, compile the model once with the Neuron Compiler, and continue using the framework as before. The output of the compiler is called a NEF file. During inference, the Neuron runtime will load the NEF file into the inferentias available in the system. And from that stage, you can start running your inference workload. We have already integrated the Neuron runtime into the supported frameworks so that apart from the one-time compilation step, users continue to use the framework as before. For those of you who would like to further optimize their models, we provide a set of tools, including a TensorBoard visualization to help you trace how models are deployed in the hardware, as well as profiling and debug utilities. At this point, I'd like to dive in and cover a few important capabilities that were designed to allow developers to focus on optimizing their applications and scale inference workloads as seamlessly as possible. The first example of that is called smart partitioning. Smart partitioning automatically optimizes neural net compute and decides what parts of the model graph will run on the Inferentia chips and what parts are most suitable to execute by the framework. AWS Neuron is aware of the system resources and is able to partition the neural net graph intelligently so that the most demanding compute operations run on Inferentia, while other operations that run more efficiently on the CPU end up partitioned to the framework. This system capability is a pragmatic approach to running inference workloads in the cloud and allows developers to fully utilize the system and increase overall performance. Many developers told us that although training models in FP32 is time-consuming and expensive, the advantage is that it provides the best accuracy. But 32-bit compute is expensive and high in power consumption, and it's really hard to move to lower 16-bit floating point or integers to optimize cost. We solved this problem with neuron capabilities, a neuron capability we call FP32 automatic casting, or autocasting in short. AWS Neuron and Inferentia are the first ML accelerators in AWS that can take a trained 32-bit model and run them at the speed of 16-bit using bfloat data types. This conversion happens automatically in hardware and is enabled by default. It allows you to keep your high-precision trained models and seamlessly run high-throughput inference, enjoying the speed and lower cost of a 16-bit data type. We already have users that reported back to us that inference accuracy is only reduced by a fraction of a percent for the models they run, so we encourage you to try it out. Next, let's talk about NeuronCore Pipeline. Customers that are running real-time inference applications like search or voice assistants are constantly looking for ways to increase throughput, but keep the latency of each inference call low so they can maintain a high level of interactiveness with the application, with their application end users. With CPUs and GPUs, this usually means that they are forced to run one inference at a time, or as we know this as batch one, which typically solves the latency constraint, but it does come at a high cost because running one inference at a time yields low throughput and low utilization of the underlying hardware that leads to higher costs. To solve this problem, Neuron and Inferentia implements a unique performance optimization mode that provides a new way to achieve extremely high throughput while keeping the end-to-end inference latency bounded. Let's dive deeper into that. With NeuronCore Pipeline, the entire model will be stored on the cache memory attached to each neuron core. Neuron cache memory is about 5x faster than the latest available HBM memory that you will typically see in GPUs. Neuron intelligently shards the model across multiple neuron cores and can scale up to 64 neuron cores on the largest instance size. Once the model is fully loaded into the cache, Neuron runtime starts sending the inference calls that in turn are streamed across the neuron cores. Each core calculates its part of the model and passes the results to the next neuron core in the chain. Using this technique, Neuron completely avoids the off-chip DRAM memory and produces high-throughput inference with bounded latency that is especially effective, as I mentioned, for models that are memory-bound, like natural language understanding models. One last note, from a user perspective, once enabled, all the available neuron cores in the system will appear as one large virtual device to the framework. So from the framework level, this is completely transparent. So now that we discussed how NeuronCore Pipeline works, let's also discuss NeuronCore groups. NeuronCore groups enable application builders to concurrently deploy multiple models to optimally use the hardware resources by running different models on each of the groups. It is very flexible, allowing you to optimize the hardware utilization well. You can run the same model in parallel on multiple neuron cores or run separate models on groups of one or more neuron cores. For example, when different neural networks need to run as a pipeline of a given input, like is usually the case with applications that require decoding and encoding data, users can define groups in different sizes to best fit their pipeline execution flow. This feature is used by Alexa text-to-speech, and I will discuss this example in detail soon. Next, let's talk about the Neuron Runtime. Neuron Runtime is a user space application that provides developers with flexibility to deploy their inference applications and optimize model serving for the specific application needs. Its basic operation is to take compiled models, also referred to as neuron executable file formats, NEF, and load them into the Inferentia chips to execute the inference requests. As I mentioned before, it is already integrated to the frameworks and in many cases seamless to the users. But it also provides the ability to control how a model is deployed and how the inferences are executed in the system. For example, batching. It usually runs in the background as a service and using a default socket to interact with the frameworks and serving applications. For containerized applications, it is recommended to deploy the runtime as a separate container. This gives you the flexibility to run the framework server in a separate container and control privileges in the system. A Neuron Runtime container is available over the AWS ECR repositories and can be used directly. You can also build your own using the Neuron packages and instructions on the GitHub. Running in a container environment allows you to attach specific inferential devices to each application container and run different inference applications in parallel. As I mentioned, the Neuron GitHub contains examples and how-to deployment guides, and more deployment options are coming soon from Amazon ECS, EKS, and SageMaker. The third component of Neuron are the tools which include utilities to help developers increase their visibility into inference execution and help improve the overall application performance. The tools include the Neuron TensorBoard plugin that provides useful information related to the Neuron devices, such as compatibility, where it visualizes which operators are supported on the Neuron devices, and profiling. For example, you can use it to view how the graph, you can view the graph and see how a flame graph showing you how much time each operator is running for. It also preserves TensorBoard's debugger plugin, which may be useful in finding numerical mismatches. Next, I would like to spend some time on the Neuron Roadmap. But before we jump into that, it's interesting to look at the performance progress we made since we launched, both on sheer throughput percentage improvement, but also the cadence of the releases themselves. Since launch, we released a total of 3 Neuron versions. With each one of them, we added new features, fixed issues, and improved inference performance by up to 64%. We fully plan to continue and have regular cadence of Neuron SDK releases. While Inferentia and Inf1 instances are already the best cost-to-performance inference in the cloud, we know that with more optimizations to the software, we can help you get more out of the Inf1 instances in performance, breadth of models supported, and additional features. To stay up to date with Neuron releases, follow us on Twitter, watch the GitHub repository or our developer forum. Along these lines, let's discuss our roadmap. The AWS Neuron Roadmap is available on the GitHub, on the Neuron GitHub site. It provides visibility onto what the team is working on in terms of functionality and performance improvements. And I hope this will help you better plan how to use Neuron with your applications. The Neuron team is constantly working to add features and improve performance. Like we discussed in the previous slide, the most recent release improved performance by 63% compared to the previous release for convolutional networks. Neuron Roadmap is divided into 3 categories. The first one is we're working on it. In this category, it means that it's in progress, but further out. We might still be working through the implementation details or scoping stuff out. It's great to get feedback. It's a great time to get feedback from all of you for items that are in this category. This will help us, of course, tweak Neuron to your own needs. You can provide the feedback directly on the roadmap item. You can just +1 it, or contact us via the developer forum. And for more complex requests, you can submit a GitHub issue. The next category is features that are coming soon. This means that those are nearing completion, likely being planned for an upcoming release. Think something around 2 to 3 weeks out, give or take. And completed, of course, are features that are feature complete and supported by Neuron. In the coming soon category, I'd like to highlight that we plan to enable object detection applications with the Inf1 instances. We initially plan to support mask RCNN, and SSD and other models will come after that. We're also planning to provide the source code of Neuron's integration into the frameworks. That will enable users to adapt Neuron into their own custom environments. Our SageMaker EKS and ECS teams are working and planning to include support for Inferentia soon as well. Now that you have a good grasp on Inf1 instances, Inferentia chips, and Neuron software, let's review how Alexa adopted Inf1 instances to improve their text-to-speech application. Alexa voice assistant is using machine learning to generate voice output from input text. Alexa speech generation requires real-time synthesis with minimum possible latency. Think order of tens of milliseconds. Otherwise, the users will perceive this as a unnatural dialogue system. Alexa is therefore processing the text to be played back to the users in chunks. And while the first chunk is playing at the speaker, the system continues to process the following chunks and send them to the speaker. This means that the system needs to process the inference at least an order of magnitude faster than the playback time. And this is end-to-end, including the network latencies, to ensure the speaker output will come complete and will not have delays between the chunks processed. In the text-to-speech domain, there are 2 types of problems to address. The first one is context generation neural network, which is mostly memory-bound, and speech generation voice coder, also referred to as vocoder, neural network that consumes 90 billion operations for every 1 second of generated speech, which makes it, of course, a compute-bound problem. In the past, Alexa used GPUs with our P3 and G4 instances to complete their text-to-speech pipeline. P3 delivered the highest throughput and lowest latency, while G4 were cheaper, but at the cost of higher latency. GPU inference added significant operational costs, so Alexa team started migrating to Inferentia. Granted, the migration to Inf1 required an effort, but it was bounded because the production engine is using CPredict API integration linked to MXNet to execute the machine learning workload. They were also able to use Python to experiment and profile their workloads with different settings. And once they found the correct ones, they were able to implement them into their CPredict API code. Since MXNet framework is natively supported by Neuron, to get to a POC level was a matter of compiling the models to be able to map them to the Inferentia chips, and they were running the POC. With the FP32 trained models, the 16-bit quantization poses a risk on the quality of the output speech. Alexa did experiments with both retrained FP16 models and bfloat autoconversion to find the best configuration and avoid quality loss. Here's the final architecture that Alexa landed on. They created a system that used two Inferentia chips that proved most efficient for their application. The first Inferentia chip is running the context generation neural network. As you might remember, this is a memory-bound neural network. Using NeuronCore Pipeline, where the model is sharded between the 4 neuron cores, running completely from cache, provided them the best performance and lowest latency. The second Inferentia chip is in turn running the 4 parallel vocoder models loaded to each of the neuron cores, running inference processes in parallel to achieve maximum throughput. To avoid any of the neuron cores running idle, the entire inference process is pipelined between the Inferentia chips. Once the first chunk finished running through the context generation and moved to the vocoding model, the second chunk is already being processed by the first Inferentia chip. As a result, TTS can run 4 parallel TTS processes serving customer requests. Let's talk about performance. Alexa conducted a few tests to compare Inf1 with the GPU instances they were using. In this test, they ran Alexa traffic, which is mostly constructed of short sentences. You can see Inf1 cost is 45% lower than P3 and 20% lower than the G4 cost, and latency is almost like P3 and of course lower than G4. Another test was done for long sentences. These are used when Alexa reads an article. This is mostly a streaming use case. In this case, we see the cost improves even further. This is because utilization is higher than the case of short sentences. We see Inf1 is 55% better cost compared to P3 and 29% better than G4 per inference. Latency is not marked here because this is a streaming application, so latency is not a hard consideration. Lastly, Alexa is projecting further improvements in neuron software, as well as their own pipeline Inf1-Architecture will continue to improve their cost and reduce latencies, putting Inferentia-based solution lower in both cost and latency compared to any GPU instance on AWS. This brings us close to the end of the presentation, but we are just getting started. Inf1 instances are available in US East 1, North Virginia, and US West 2, Oregon, today. We plan for a broader global rollout very soon, and like the rest of the accelerated compute instances, the Inf1 instances are available in the standard EC2 purchase options, including on-demand, reserved 1 year and 3 years, and spot pricing options. They are also available as part of the EC2 saving plans. Customers who have application dependencies on NVIDIA libraries can continue and use G4 to receive a good cost per inference outcome. The rest of the customers, either running on G4 or on CPUs today, would get the best performance and lowest cost by using Inf1 instances featuring Inferentia. I hope you will all give it a spin. Thank you very much.